Alright, hey everyone, we're live. So today was Codeforces Round 878, which is a Div 3 round. Right now, assuming that nothing I do gets hacked, I am in second place, which is pretty good, although I definitely think that... Well, no, I definitely could have done several of these faster, and these penalties on G were kind of silly, but in any case, that's where we are, and so we'll be going over the solutions just in order A through G. So I think we'll just get started. Okay. So for problem A, we have an unknown string consisting of lowercase letters encrypted such that for each character, we're going to put that character into S. We're going to add some number of letters other than the letter from A, and then we're going to add the original letter again. And so we're given the encrypted string, and we just have to decrypt it. So the idea here is that the first character of S must also be the first character of A. And then from there, the next appearance of the same character corresponds to the second encryption step. So what we're going to do is we're going to look at the first letter, we're going to add it to A, so here we know that the first letter of our answer is this A. And then we're going to move to the next A in the string. And then now we're just going to repeat that process. So the next letter is C, that's the next letter of our answer, and then we're just going to go to the next C. Okay. And so the code for this is pretty simple. We just read an N in the string, and then I maintain like the position we're currently at. And so then until we reach the end of the string, I maintain the current letter C, and then I iterate until we reach the next copy of C, and then I add C to our result string P. Okay, that one's pretty quick. So problem B, we have a cafe with K desserts. The desserts are numbered from 0 to K minus 1, and dessert I costs 2 to the I coins. We have to find the number of combinations of desserts we can buy that will cost at most N coins. So the key observation here is that the set of desserts we buy corresponds to the ones in the binary representation of their total cost. And so the implication of this is that with K desserts, there is exactly one combination of desserts with any cost from 0 to 2 to the K minus 1. And so for example, the only way to create a combination with cost 3 is to use desserts 0 and 1, because 3 is equal to 2 to the 0 plus 2 to the 1. Okay. Now, since we can only buy desserts with cost N, this tells us that the maximum cost of any combination we can buy is the minimum of N and then 2 to the K minus 1, which is the maximum cost of any combination of desserts. And so since there is exactly one combination we can buy for each cost from 0 to the minimum of N and 2 to the K minus 1, that tells us that there are min of N plus 1 and 2 to the K combinations in total to choose from. And so this expression is our answer. Now, an important thing to note is that if you shouldn't calculate 2 to the K explicitly if K is too large, because if K is for 10 to the 9, for example, in C++, computing 2 to the K is going to give you overflow even if you use a long. And in Python, computing 2 to the K, I believe, is going to be too slow. So what we will do is we'll check first if K is less than 40, and then if N is greater than or equal to 2 to the K, then we know that the answer is 2 to the K. And otherwise, it's N plus 1. Okay, so that's how this problem goes. I'll take questions as we go, but for now, I'll move on to problem C. So for problem C, we have an end-day vacation, and we want to allocate K consecutive days or more to go skiing. But we're restricted under the constraint that we have this array A of the temperatures for each day. And we can't allow the temperature to be greater than Q degrees at any point during the skiing trip. So we have to pick the number of possible intervals we can choose. So in other words, the number of intervals of at least k such that no AI, or of length at least k, such that no AI within that interval has value greater than q. Okay, so hold on, I'll take a few questions real quick. So Sarthak asks, will this be saved as a VOD to watch later? Yeah, if you go to the live section of my channel, you'll be able to see this stream as well as all of my past live streams. And Sankesh asks, what does plus 1 plus 2 mean in the result? Plus means that the problem was accepted, and if there's a number afterwards, then that number is how many incorrect submissions were made before the correct final submission. Okay, so as far as the solution to this problem, let's say we want to count the number of valid intervals ending on day I. So in other words, we need the number of intervals of length at least k, ending at I, and containing no positions where AI is greater than q. So what we're going to do is we're going to say j is the last date before or including I on which the temperature was greater than q. And so what this means is that if we want to end at I, and now we can't use any dates before j, so that means that we can only use dates in j plus 1 through I if we're trying to count intervals ending in I. Okay, and so if this interval has length less than k, then we can't construct an interval of length k ending at I that doesn't go through j. And if it goes through j, then it's invalid because we have the date on which the temperature is too large. So now let's say that I minus j is greater than or equal to k, so the interval has length at least k. Now, any interval contained in j plus 1 through I with length at least k will be valid. So we just need to count how many such intervals there are. Now, the smallest possible length of such an interval is k, and the largest possible length is I minus j. So we need to count the number of valid lengths from k to I minus j, which we know is I minus j minus k plus 1 possible intervals. And so that gets us the answer for a fixed I. And so then to solve the original problem, which involves counting over all I, we iterate over I and maintain the current value of j as we go. And so to demonstrate what my code looks like, so I read in nk and q, and then so I read in the array, and then I iterate over I. If a of I is greater than q, I set the last value to I, and then afterwards I add the maximum of 0 and then I minus last, which represents j in my notes, minus k plus 1. And then that gives us our answer. Okay, so that's problem C. I'll pause for a moment to see if anyone has questions about the problem so far. And I'm also going to check actually real quick if there are any going on. Looks like there's a hack case on F, which I'm a little bit worried about. Well, here, let's see what people did. Looks like it was solutions that were pretty close to the time limit beforehand. Okay, Kumar asks, does using 2 or 1 and then bit shift k rather than 1LL bit shift k matter? So it does for my solution, and the reason is that I've just checked, to be a little conservative, I've just checked if k is less than 40. And so because 2 to the, I believe 31 is the largest, I think No, I guess 2 to the 30 is the largest power of 2 that a regular int can contain. And so if k is greater than 30, then 1 bit shift k will be stored in an int, and so it'll overflow. On the other hand, we don't really need to worry about powers greater than 30 because 2 to the 30 is greater than the largest possible value of n anyway. So if you wanted to, you could instead do if k is less than 30, and then you don't need to worry about long longs. I believe that would work. But in this case, it matters, but only because I'm working with slightly larger values of k. Yeah, I'm kind of curious because I technically, yeah, I wasn't super rigorous about proving my solution to f, so I'm a little bit worried that there might be something weird going on there. But it looks like most of the solutions, or all of the solutions really, that are being hacked were pretty slow already. So maybe it's something different. It doesn't look. None of these really look that much like mine. Okay. Anyway, let's move forward. So, for problem D, we have a workshop with 3 carvers, and n people are going to come to the workshop looking for a toy with some pattern numbered from 1 to 10 to the 9. Each carver is going to choose their own integer pattern, and making a toy of pattern y for a carver who has pattern x will take the absolute value of x minus y time. And we want to find the minimum, or we want to find a way for the carvers to choose their patterns such that the maximum waiting time over all people is going to be as small as possible. So for this problem, we're trying to minimize the maximum time consumption. And so as is typical for problems where we want to minimize the maximum, we're going to binary search for the answer. And so in other words, we want to tell whether we can achieve a maximum waiting time of at most t. And if we can, then we know the answer is less than or equal to t, and otherwise we know the answer is greater than t. And so what that means is that we can binary search for the smallest possible t that works. Okay, so if we want to set the waiting time for everyone to be at most t, that means that for each a of I, there must be a carver in the range a of I minus t to a of I plus t. And Hari asks, could you please explain this problem with the third example? By this problem, do you mean problem, or let me know which problem you mean. I assume you mean problem D. But in any case, whichever problem you're asking about, I can walk through the example after I go through the solution conceptually. Okay. So what we're going to do is we're going to sort A, and so then we know we need some carver in the range a of 1 plus or minus t to a of 1 plus t. And the observation here is that we can greedily place the first carver at a of 1 plus t. And the reason is that we know this carver won't be too far to the right of any of our choice, because a of 1 is the smallest element of a. And so if this carver appears before a of 1 plus t, then it'll certainly appear before a of I plus t for any other I. And so really what we need to worry about is we need to make sure that this carver is also satisfying, or is also able to make as many of the remaining choice in time t as possible. And since all the other choice have positions greater than a of 1, that means it's the best position for the carver is as far to the right as possible. Okay. So now, once we know that our first carver is going to be a of 1 plus t, we can mark all choice within t of this carver as handled already, because we already know we can make those choice in time at most t. And so now we can repeat with the smallest choice not yet covered. So that choice is going to need to be covered by some carver, and since it's the smallest one remaining, we can add t to its position. And then again, we can mark off all the choices that are handled by that carver. And so then that lets us check if it's possible to achieve a maximum waiting time of at most t, then we know the answer to the problem is at most t. Oh, it looks like we've got a bit of spam in the chat. Hold on a sec. Okay. So, all right, and so then this solves the subproblem of our binary search in O of n time. And so after we've sorted A, and so that tells us that we have a solution to the overall problem in O of n log max time, where max is the maximum possible answer in our binary search. So I show you my code, and Katuri, this may answer your question as well about how we deal with the 3 variables while using our binary search. So what I'm going to do is I'm going to read in my integer, or my integers in the array A, and then I'll sort it. And so then I'll take the low value and the high value of my binary search to be 0 and 2 times 10 to the 9, because, and this is definitely higher than any possible answer, because if we have a carver, or if we have 2 times 10 to the 9 seconds, then if we place a carver pretty much anywhere, then they'll be able to make all of the choice. And so then I just binary search, and then I have this helper function OK that checks whether some time that I've stored as mid is valid, is possible. And so the way I do this is I use cur as like basically the position of the current carver we're looking at, and u, which I initialize to be negative mod, something really low, so it's never going to be able to like work with any pattern. And then I have use, which represents the number of carvers we've used so far. And so then I iterate over my all of the choice, and if the current choice is at least mid apart from our current carver, so in other words, it can't be reached by our current carver in the time we're trying to achieve, then I add a carver, and again, because of my greedy observation that I made earlier, the best position for this carver is A of I plus mid. And then I return if we used at most 3 carvers. And one nice thing to note is that this problem would actually work even if like the number of carvers we had wasn't 3. Like we might, even if it said like, okay, you have K carvers you can use, for example, I could just substitute K for 3 here. Yeah, and so that's how this one goes. Min at says for problem D, I iterate from 1 to n as the first carver, and binary search from I to n to find the minimum result possible for the 2 other carvers. Yeah, I think that probably makes sense. I need to think about it in a bit more detail. Let's see. And so Katuri asks, how do we know where we should start? So, okay, so this is the key idea here within the binary search is this greedy observation. So if we sort the carvers in ascending order, then when we look at the smallest carver, A of 1 is the smallest carver, or is the smallest choice, I should say. We know that to achieve a time of at most t, we're going to need to have some carver between A of 1 minus t and A of 1 plus t. And so afterwards, if we need to figure out, okay, where can we place a carver within this interval to handle as many of the higher numbered choices possible? And the observation is that the best way to do that is to place the carver as far to the right as possible, so A of 1 plus t. And the reason is that all the other choice are further to the right, and so the issue isn't going to be this carver is going to be too far to the right. We're worried about the carver being too far to the left. And to make that as small of an issue as possible, we're going to place the carver as far to the right as possible. Okay, so So there are a couple of people asking about using dynamic programming for this problem. In particular, someone's proposed a DP in which DP of I of k is the minimum cost to deal with, or such that the first k carvers handle the first I positions. I believe there might be like some clever optimization you can do, but my understanding here is that if we do DP of I of k, or so I'll do it, or equals the minimum cost such that, or the minimum cost, or the minimum max time of making the first I choice with k carvers. My understanding is that the transitions, they're going to be O of n transitions for each state with this DP. So that this would take O of n squared k time. Because for each possible, like, I, we would have to consider all earlier positions the carver, or I guess all earlier positions the current carver might cover. And so O of n squared k would be too slow for this problem, and so, which is why we use binary search. But in general, my advice is that anytime you have a problem where you're trying to like make the maximum of some numbers as small as possible, or alternatively make the minimum of some numbers as large as possible, that's usually a clue that binary searching the answer is the way to go. Okay, and DKIJB mentions that we only need to consider unique elements in the array. Yeah, that's correct, but it turns out not to meaningfully improve the complexity of our solution. Man, looks like Physics 0523 is trying to trying to have the most hacks this contest. It's interesting to see. Yeah, we'll see. I'm worried I might get punished for not proving my solution rigorously, but we will see. Oh, looks like someone got hacked on, oh, this is interesting. What's the hack here? Yeah, this is interesting. I'll be we'll have to see what ends up happening. I'm a little bit worried about this, but I guess we'll find out later. Okay, anyway, let's look at E. So we have two strings of equal length, S1 and S2, and an integer t. So we have to answer Q queries, where for each query, we might have to block the characters at some position for t seconds. We might have to swap two characters, which are unblocked, and then we have to determine if the two strings are equal at the time of the query if we ignore the blocked characters. So we have up to 2 times 10 to the 5th queries. Okay, and hold on, before I go over this, there are a couple of comments in the chat I want to read through. So first of all, someone is saying that if we sort the array first, we can check if t is the possible answer in big O of log n by checking the distance between the leftmost element that's greater than a of 0 plus t and the rightmost element that's less than the last element minus t. Yeah, so that's correct. And so the idea that this person is suggesting is, so like I suggested here, we can greedily place the first carver at a of 1 plus t. And using a similar observation, we know we're going to need to cover the last carver, or the last choi, with some carver. And the best way to do that, to cover as many other choi's as possible, is to place the carver at time a of n minus t. And so what we can do is we can find the first choi not covered by the first carver, which is the first, so in other words, the first choi with pattern at, or greater than a of 1 plus 2t. And likewise, we'll find the last toy with pattern less than a of n minus 2t, and that'll be the last toy that we need to cover with our middle carver. And so then the middle we can, so then we can check if these toys can be covered with one carver. So in other words, if their distance is less than 2 times t. Yeah, so that's another valid solution. And Viniac asks, what is this hacking thing? Can you give a brief explanation if possible? Yeah, so after a Division 3 or Division 4 or an educational round, there's a 12-hour phase for hacking, and what that means is that everyone can look at everyone else's code, and then you can submit test cases to try to break it. And so what that means is, like, if I wanted to hack my F, which I'm worried someone might want to do later on, I can just, like, enter a test case that I think will break it here. Let's just say, I don't even remember what the input format is. Let's just say, I don't know, I think that this test case is going to break my code. So then I would click hack, and then my code will be run against that, my code will be run against that test, and if it fails that test, then I'll lose credit for that problem. And so it's basically a chance for people to challenge other solutions by creating inputs that they think will break their code. And here you can see I got invalid input because my test case was not formatted correctly, but that's an example. Yeah, so and Light Yellow asked, do you miss CodeJam? Yeah, I think it's a bummer that Google CodeJam is gone, but oh well, what can you do? Hopefully it'll come back, or there will be other similar contests that come up eventually. Someone's asking, do I know why many Java solutions are being hacked? Let's see, can I filter by language, I wonder? I mean, so it seems like most of the F hacks are on solutions that were pretty close to the time limit to begin with. Actually, okay, why don't we hold this question, and then I'll talk more about this when we talk about F. And also, if you could clarify, if you're, it'll help to know whether you're asking why are so many Java solutions being hacked in this particular contest, or like why do Java solutions get hacked in general. But anyway, we'll talk about that when we get to F. So let me explain the solution to E first. So what we're going to do is we're going to maintain the set of unblocked positions at which S1 and S2 are not equal. And this turns out to be pretty easy to maintain for all 3 queries. So for type 1 queries, we just have to block a certain position for t seconds. And so we'll remove the position pause from the set if it's currently in it, because now it's blocked, so it can't be an unblocked position at which the two strings don't match. And potentially add it back if necessary after t queries. Okay, so for type 2 queries, we're just swapping 2 positions. So what we're going to do is we're going to remove pause 1 and pause 2 from the set if they're currently in it, perform the swap, and then add pause 1 and pause 2 back if necessary, if they don't match. And the idea here is that if we swap pause 1 and pause 2, none of the other positions are being affected, and so nothing is going to change. We just need to make sure, we just need to update whether pause 1 and pause 2 should be contained in our set. And then for type 3 queries, we just need to check if the set is empty. And if not, then there's an unblocked position at which the 2 strings are not equal, and so that means that the answer is no. So, and so this is an O of n log n solution. Technically, you could implement this using like an array and then just maintaining the number of elements, or like an array where you check is each element in unblocked position where the 2 strings mismatch. And then you can maintain the number of positions in this array that are true. And if you do that, then you can make this work in O of n instead of O of n log n, but that's not necessary to get a C. Yeah, so I'll show you my code real quick and then we'll move on to F. So we're going to read in the 2 strings and then maintain our set. I'll initialize our set to contain all the elements at which 2 strings don't match. And then I have this queue where I store basically all of the positions of, or where I store all of basically the blocked elements that we need to unblock. And so if there's an unblocked element that we need to unblock for our current query, I'll unblock it and I'll add it back to our set if necessary. And then otherwise I process our queries. So for the type 1 queries, I mark this position as something we need to unblock after a certain amount of time, and then I remove it from the set if it's contained in the set. If the type is true, then I read in the indices of the strings and the positions. I perform the swap, and then for each position that we changed, I erase it from the set if it was in the set beforehand, and then I check if it should be in the set after this query. And then to handle the queries, I just check whether the size of the size of the set is 0. Okay. I'm gonna answer all of the hacking related questions after I go over F, because after I explain the solution, or at least what I think is the solution to F, I'll go over I will go over what I think like the hacking situation might be. Oh, and Prashant asks, I use rolling hash to solve E. Is that a fine solution to this problem? Yeah, I suppose that would work. I think it's probably, correct me if I'm wrong, I suspect the implementation is significantly more annoying than this was. So, like, I think you can make that work. It would just be kind of a pain. But I can see, like, what the general idea would be. Because if you have, like, a polynomial hash and you maintain all of the powers you need, then you could essentially, like, delete characters from the string or perform swaps efficiently. And so yeah, I think that would work. I do think it would be harder to implement. But I mean, it seems like a fine idea to me. If you like get hacked or something or get wrong answer, one like possible explanation, or you should make sure that you're actually using. Well, I guess here, I don't know if the birthday paradox is going to be that big of an issue actually. So maybe just one prime would work. But anyway, yeah, if implemented correctly, I think hashing works here. Okay, so let's go over problem F. So I'll start by presenting, this is like the general solution idea, and I think like implementing this naively is probably why people are getting hacked. Yeah, Prashant says they use double hash, so yeah, I think that probably should work totally fine. Okay, but anyway, so what we're going to do is we're going to consider an array OK of t of ij, representing can we reach the position ij at time t. And so initially, OK of 0 of ij is false for all ij except 0, 0. And so now we're going to show how to compute OK of tij if we know, like, OK at t minus 1. Oh, sorry, I forgot to explain the problem. So, first of all, so we have this n by m grid where we need to get from 0, 0 to nm. Each second, we can either not move or we can increase one of our 2 coordinates. But there are times at which one coordinate, either vertically or horizontally, is going to be shot. And we can't be at that position at that time. We have to find the minimum time for the character to reach the desired point. Okay. And Nalin says like that DP is essentially what they did and they got hacked. Yeah, we're gonna talk about things you need to do. I think that you need to do to get this accepted in a moment. Okay. So okay, so to compute OK of t at time t given OK of t minus 1. So first, if OK of t minus 1 of ij is true, then that means we can either stay there, so we can go OK of tij. We can go up I by 1, OK of I plus or ti plus 1j, or we can go increase j by 1. So we'll set all of these to true. And then we'll iterate over the railgun shots taking place at time t and update the corresponding OK of tij values to false. So in other words, for example, if all the coordinate I equals c is shot, OK of tcj will be false for all j. So our answer is -1, or is the lowest t at which OK if t n m is true, and -1 if no such t exists. But iterating over t like up to infinity, or even over all t up to like 10 to the 9, the largest time any railgun shot could occur, would be impossible given the time constraint. So the trick is to stop to stop iterating as soon as we reach the position nm, or as soon as OK of tij is false for all ij. And my suspicion, I thought about proving this, and I think I have some general intuition for why this is true, but I don't have a rigorous proof. I believe that one of these two things is guaranteed to occur within O of n plus m plus r time. And my intuition here is that each railgun shot should only stop us for like for 1 second, or like a block of k railgun shots should only be able to hold us in place for k seconds. So I think this is true. It might be that like the complexity is O of n plus m plus r squared, which is also fine because each iteration takes O of nm time. So this gives a complexity of O of n squared m plus nm squared plus nmr, or maybe nmr squared, which is fine as well. And all of these terms are at most 10 to the 8th, which should be fine because we have 1 second. And the other thing is that our iteration is just performing updates on this array, which is like very efficient when we think about it from a cache perspective. And so my code runs in 15 milliseconds on pretests. Now the other thing you have to do to get accepted on this is you have to, we need, rather than building the entire 3D array OK, we'll include only the second 2 dimensions and iterate over t in place. And so what I mean by that is I'll showing my code. Here, in my code, this array is called viz. And so viz is just n plus 1 by m plus 1. And then for each t, I just update which positions are visible in place. I don't include the t dimension. And that's because, so if t can be up to like 10 to the 4th, and then n times m can be up to 10 to the 4th as well, this could like easily MLE. And so I think that's required to get accepted. Sorry, let's see. Not letting us ask, isn't it the same thing considering time complexity? What you said should optimize memory, isn't it? So I might not be answering the question you're asking. So if this isn't what you're wondering about, let me know. But this complexity is fine for time. And we can also get it, and we can use this observation to get the same memory complexity. But this memory complexity is not sufficient to solve the problem. Because because declaring 10 to the 8 ints would take 400 megabytes, which is too many. So the memory complexity actually is tighter than the time complexity in some sense. And Harsh asks, how did I get all the problems on one page? So I went to problems, and I clicked complete problem set down at the bottom here. Yes, that's how you can do it. Let's see, and I want to see it. And so now I'll talk briefly. I don't know, one thing I'm worried about is I don't have a super rigorous proof of the claim I made. It's intuitively true, and there will probably be a proof in the editorial when it's out, and I'll actually check real quick if it's if there's an editorial yet. Let's see. Looks like this person has the same solution. I wonder if they implemented the DP in Oh yeah, looks like they got hacked. Oh wow, and their solution actually was fast on the pretest. I wonder what happened here. Looks like they used a bit set. How many bits are in here? 1, 2, 3, 4. Interesting. Anyway, we'll see. So yeah, so anyway, so we'll watch and see what the hacking situation looks like. If this claim turns out to be false, then it's possible that my solution could be hacked. And so I think like some people had alternate solutions, and so I might take those. I'll go back now and answer the questions people had about hacking. So Ami asks, how do I know if my solution got hacked? Do I lose my points if so? So I believe you'll get a notification here if your problem or somewhere up in the top right if your code gets hacked. And then if it does, then you do lose credit for that problem. And then going back to Skiho, I don't know if I'm pronouncing that username correctly, but asking why Java solutions get hacked. Probably, so the most common reasons are, first of all, like Java just has a high time overhead in general, and so there are a lot of Java solutions that might like just barely pass under the time limit in contest, and so the hacker may have a slightly harder edge case that they use to hack the Java solutions. More frequently though, when I think of people getting hacked for using Java, the most common reason that I can think of off the top of my head is that the arrays.sort function in Java uses quicksort, which is O of n squared time in the worst case. And so a lot of people have like hack cases prepared where they'll make quicksort TLE. And so because of that, if you're using Java, you have to make sure to either use an array list and use collections.sort, or you can shuffle your array randomly before sorting it, and then that'll get the quicksort. And then that way, quicksort will be operating on a random array, and so the n log n complexity will work. Yeah, okay, so I'll look at a few of these hack solutions and see if I can guess what's going on here. A lot of the ones that I look for, I think that what physics is doing is they're sorting by so physics is sorting by the longest time or the slowest solutions first, and so he started by hacking a lot of the like solutions that took like 900 milliseconds, and now he's on some faster ones that it turns out can be hacked. Let's see. So it looks like most of these solutions that are being hacked seem to involve, well, let's see. What's RR? Yeah, so my thinking is that it seems like most of these solutions are getting TLE essentially because the implementation is a little inefficient and ends up using more memory than it should. So, and so what I mean by that is, let's see, what does this person have all of this code in here? You do not need a Fenwick tree for this problem. Oh, interesting, this person is doing binary search of some sort. Oh, this is not F. Why am I looking at these problems? Okay. Anyway, so my suspicion is that like a lot of people are doing a similar idea where they use a queue to store all possible positions, so where a position is I, J, and T. And here, because there could be up to like 10 to the 8 possible positions, this will require adding 10 to the 8 elements to a queue. And that is likely to TLE just because the constant factor associated with using the queue. And so if my solution, assuming my solution doesn't get hacked, assuming my claim is true, then this is likely to be more efficient than the other solutions because I'm just like updating this array viz in place, and I'm not actually like instantiating a new variable for each possible state. And so because this is more efficient in terms of its memory usage, it's less likely to, or its lower constant factor is going to help prevent TLE. But anyway, I wonder if the hack case isn't public, right? yeah, I don't think we can see what the hack case is. Oh, it looks like this person is hacking in LGM now. Let's have a look and see what happens here. I sort of assume physics is just trying to hack all of the possible Fs, but it looks like it's still waiting. It might be time limit. This person was using Kotlin. Yeah, it looks like so it looks like that got hacked. That's interesting. Okay, so maybe what I'll do before and then move on to G is I'm gonna look at, I think there's an alternate solution to G that some people use that's substantially different from what I did. And so I'm going to look through and see if I can explain that as well, so that in the event that mine gets hacked, there will be an explanation of another solution. So let's look at this solution from SSRS. Okay, so what this person is doing is, so I believe for each, okay, so they're maintaining a 3D vector T, and so the outer dimensions correspond to the coordinates. And so then they're reading, and so then it looks like, okay, so for each, and so I guess they're maintaining, and so for T is storing for each pair of coordinates the set of times at which this coordinate is inaccessible. And so then they have this vector of vectors count that I guess is storing the number of times at which each coordinate is inaccessible. And then they're also storing inf and saying everything is inaccessible at time inf. And so then they have this 3D vector dp where, oh, I see, maybe this is, hold on. Okay, so then they're storing dp, and at each position, dp of jk is going to have positions, or is going to have length count jk, and then is going to be initialized to infinity. Okay, and so I think what this person might be doing, yeah, so I think this might be what this person is doing, and this is easier to prove that the complexity works. So this makes some sense. I believe what's going on here is that this person is saying we're going to let dp of I of j or of k be the minimum time at which we can reach position ij after the first k railgun shots targeting ij occur. Yeah, this is probably the intent. So this is probably the intended solution. So it might be that the claim I made is false. So we'll have to see. But anyway, and so now we can transition from dp of ijk to compute dp of ijk, or to compute like the dp for I plus 1 and j plus 1. And the complexity this time the complexity is now, so we're going to have, so for each ij, the number of states is going to equal the number of railgun shots targeting I and j. And so this is bounded above, by each rail. So if n, in the worst case, a railgun shot could target all n, m elements, which is possible if one of n and m is 1. So in the worst case, there are 10 to the 6 states. And so this is going to run efficiently. And I'm curious how they deal with the transitions. Let's see, so okay, yeah, they transition using chew pointers. Okay, and Ratan asks, how do people know which codes can be hacked? Do they check randomly? Yeah, so for a problem like F, there aren't that many people who solved it in contests. So this person might not even be reading the code. They might just be submitting this hack to every problem. And hold on, I'm going to check here. I feel like I'm going to get hacked. But we'll find out soon, I guess. Yeah, that's interesting. That's a lot of F's getting hacked. But anyway, so this solution I think is the more clearly provable one, and so this is a good reference if you're trying to figure out, or if you're thinking of if you're looking for a solution that's provably correct. Okay, and Carvallian asks, did you explain A? It was kind of brain numbing. Yeah, so that A was at the very beginning of the stream. Okay, anyway, that's all interesting to see. Yeah, so we'll wait on this. I'll try and wait to end the stream until this guy tries to hack me. How many solutions were there to this problem? I want to know how long it'll take. About 171, and then 100, he's hacked a bunch of them already, so. Okay. And Carvallian asked, do you think A was hard? I would say it wasn't like especially hard compared to usual A's, but I do think that the problem was maybe not the easiest to read. Like the statement, I think, is not as clear as some of the other ones I've seen on Codeforces, so that could make it a little bit confusing. And Not Linux asks, for the SSRS solution to F, how do you do the transitions? So we do the transitions using chew pointers. So we're going to basically, so P1 here is storing the position in DP of ij, and P2 is storing the position in DP of ij plus 1. And basically we're trying to figure out, for each of the possible positions in the second array, what's the earliest that we can get there, or what's the earliest that we can get to that position after the corresponding railgun shot. And so we can increase the pointer corresponding to whichever time was larger. Ratana asks, what happens to the person who got hacked? They lose credit for solving the problem. Okay. So let's do G now. Okay. So we have a circle divided into n sectors numbered from 1 to n. We initially don't know how many sectors there are or how they're numbered. They're numbered arbitrarily, like not necessarily in increasing order. Initially, we can tell the number of the sector to which an arrow is pointing, and then we can move the arrow k sectors counterclockwise or clockwise, and we can find out the new number of the sector to which the arrow is pointing. And in the hard version, we can do this at most 1,000 times. In the easy version, we can do this up to about 2,000 times. We have to determine the number of sectors by the end, or after however many queries. Okay, so at first this might seem impossible. Like, the most obvious thing to do would be to just keep going one step to the right, and then if we see the same number from our first sector, then we know we've made it all the way around the loop, and so we can tell what the value of n is. But of course, this is only going to give us information about the first 1,000 sectors here, so this won't be effective if there are more than 1,000 sectors. In general, though, to confirm what n is, or to show that that we actually know we found all of the sectors, we probably do need to visit the same sector twice. And so we know we need to in some sense use large enough values of k, or skip by large enough numbers of sectors to actually get information about all n sectors. But the problem is, for example, if we were to repeatedly move 1,000 sectors counterclockwise, then we might just skip over our first sector without knowing this. And so an example is if n is 999, then if we repeatedly skip by 1,000s, we would visit sectors 1, 1,001, 2,001, and so on up to 999,001. And then afterwards, we would get up to sector 1,000,001, which because n is 999 would be sector 2. And here we wouldn't know if there were 999,999 sectors, or if there actually were, for example, 999,998 sectors. And so this ends up becoming really messy and is also infeasible. So, and Carvallian asked, by the way, can you list these streams? I'd love to access these at a later point in time. If you go to my channel and then you click live, you can see an archive of all of the past live streams. Okay, so basically we want to skip large enough numbers to visit all n sectors, but at the same time we want to know if we've actually passed the beginning of our array so we can tell what n is. So what we're going to do is we're going to combine the two general approaches I've given so far. So what we're going to do is we're going to pick some k and start by visiting the first k sectors. If n is less than k, then we'll reach the beginning of the circle again, and we can tell what n is. Otherwise, for our remaining queries, we'll repeatedly move k sectors clockwise. And if after some query we pass the beginning of our circle, we'll see one of the first k queries, and we'll know where we are. So we'll see one of the first k sectors, and then we can tell where we are. And so this lets us figure out where the first sector is relative to our current position, which is enough to compute n. Now, if we think about like whether this will use few enough queries, suppose we can use q queries. So our second step, move k sectors per query, and we have roughly q minus k queries. So this works for n up to about k times q minus k. And it turns out that this is maximized when k is about q over 2, so we use about half of our queries on each step here. And so this works for n up to about q over 2 times q minus q over 2, which is q squared over 4. And so when for G1, this works for n up to 10 to the 6, and so this is a valid solution. For G2, though, this approach only works for n up to about 250,000, which is not even close to being good enough. Okay. And Jasonic asks, I just did plus current sector until we can deduce the sector count, and I don't know why it doesn't really work. I think basically the issue you might run into is that you could like jump past the starting sector without really knowing it. And so like you don't have a good way of checking whether you've passed sector 1 again. Okay, so as far as how we can adapt to to G2, for these sorts of interactive problems, and especially ones where the solution is fixed initially and isn't like adaptive, it's not changed depending on the queries you do, randomness is often really useful. And there's actually a clever way to take advantage of it here. One useful property of like getting the numbers of each sector that we visit is that the number of a sector gives us a lower bound on the total value n. So in other words, if we see like that we're at sector x, we know n has to be greater than or equal to x. So what we can do is if we query m for some number, m sectors chosen at random, then we'll get their numbers will be m values distributed between 1 and n. And so intuitively, we can roughly expect that the largest number we see will be around n minus 1 over m. Or sorry, what am I saying? Or it'll be about n divided by m away from n. And the idea here is that like our m number is that we're roughly going to be partitioning the range from 1 to n into m plus 1 values or whatever. But anyway, so basically if we query m random numbers, then like on average the largest number should be approximately 1/m or up to like 1/m of the way further from n. And so its distance to n will be about n divided by m. Okay, and so now what we'll do is we'll move to this largest number before we start our second step of moving by k sectors each query. And the idea is that then we know that when we reach this largest number, we won't have overshot. That'll still be like less than, or that'll still be like a position less than n. Ratana asked in a div3 content. Oh yeah, okay, that question has been answered. Great. Okay, and so now since our distance from n is about n divided by m, the total number of queries this takes is about n divided by mk. And so anyway, so this means our total solution is going to be to query the first k sectors, and then we're going to query m random sectors, and then we'll move to the largest sector number we've seen, and then move k sectors clockwise until we reach the beginning of the circle. And this will take a total of about k plus m plus n divided by mk queries. And so it turns out that like the most efficient way to do this, or the most efficient solution, is to take k or equal to m to equal to the cube root of n, or approximately something like that, and then that'll give you 3 cube root n queries, which is 300 here. But a lot of possible choices of k and m work here. In my solution, I took k to be 200 and m to be 500, and so this this takes about like 710-ish queries per test case. And actually, let's see, maybe we can see how many queries I took on each test case. Yeah, it looks like here's a 733. It looks like pretty consistently I took under 750 queries. Yeah, here's a 740. Not only it says I can't get how knowing a number between n and minus, or a number between n minus n over m helps the G1 solution. So you don't need this for G1. For G2, this is helpful because then our second step is going to be faster. Because for G1, when we're moving k sectors per query, that's going to take about n over k queries to visit all the positions we might want to look at, and n over k, and so there's no way to pick k such that k plus n over k is less than 1,000. And so the reason, the reason this works for G2 is that, the reason is that now, when the distance from n is only up to like n over m, that means that if we're going like in steps of k, we're going to need only about n over m times k steps. And that, if we pick k and m to be sufficiently large, n over m times k is not going to be very many queries. So that's how that's why this is helpful. If we didn't do this step, the fastest we could solve the problem would be about 2,000 queries. So walking you through my solution, let me go through my code. Oops, hold on. I think I already have it open in another window. That's fine. I'll just open read only. So I store the first k plus 1 sectors, and then I just query +1 k times, and then read them in. And if we get back to the beginning, then we know what n is, so we can just finish there. Otherwise, this variable is my m. I use cap to store like the largest value we've seen so far. And then I'll repeatedly query a random value from 0 to 1 million, or I'll get to a random position from 0 to 1 million and then query and then see what's at that sector. And the randomness is important to make sure that like you actually have that, like, no matter what the original arrangement of the sectors is, there's a good chance that you'll end up with a high cap. Because otherwise, if you were to just keep like going +1 each time, for example, then if the sectors were numbered like 1, 2, 3, 4, 5, and so on, then your maximum number might not be anywhere near n. So, okay, so from here, I get to like our largest value so far, our cap, and then repeatedly, like while true, I just add k, and then I check, is this a value that we've seen already? And if so, then I can deduce what n is from that. Yeah, so that's the problem. And I'm going to check if I've been hacked on F real quick. Let's see. Oh, it looks like someone got hacked on G2. I kind of wonder what this is. Looks like this person did some kind of randomness. I wonder if This is interesting. So person like take random is randomly, so 600 times they're randomly picking a number and querying it, and so they're doing this. I guess this is like the M step that I did, and so then yeah, I guess they're doing something kind of similar where for one or where. Yeah, maybe this is just like a wrong implementation of a similar general idea. Gaming but not really as says, can you give some intuition about how to go about solving interactive problems in general? Yeah, so first of all, for most interactive problems, and this is obviously an exception, binary search is a good idea. Like, and especially if it seems like the complexity in terms of queries is going to be logarithmic. There are a lot of interactive problems where you use binary search. So, like, thinking about like if there's a convenient way to binary search it should be like your first thought on most interactive problems. More generally though, here, especially if the interactor is not adaptive, random or interactive problems are probably the most common use case for randomized solutions. And I'll see if I can find this. Let me see if I can find this problem. But there's this problem I remember from one of my, not this one. It was on one of my first Codeforces rounds. And let's see, not this one. Not this one. Oh, here we go. I think this is it. Yeah, there's this problem that actually really reminded, where I sort of learned the randomization trick specifically that you use for this problem, where here we're given a sorted order, or a sorted single linked list, and for each let's see, so each element is going to contain its current value and then the index of the next element, and we can get the value in the next element for each, or for a given I, and then try and give the answer, and we want to find n. And you could do a similar thing where you randomly try to find where you randomly try to find the number of elements just by using by essentially you're going to query like 1,000 elements and find the one with the largest value, and then you'll just keep going next from that until you find the last element. So that's it. So there's like this similar idea actually comes up pretty frequently. And so these sorts of randomized ideas are often useful. So that's what I would say. I would say, like, think about, like, binary search and randomization should be in your toolkit. Otherwise, I think it's helpful to distinguish as well between interactive problems where the goal is, like, getting the right order of magnitude versus interactive problems where you're, like, trying to squeeze out queries. Like, maybe you have, like, a solution that works in 37 queries and then the goal is 35. And for the first type of problem, you don't need to focus on, like, micro optimizations. You can focus on big picture ideas. For the second type of problem, it's often useful to write like a brute force DP that will, like, for small cases, solve the problem in like the minimum possible number of queries, and that can often like shave off the query or two that you need to get AC. So those are, like, I think the general tips of interactive problems that don't necessarily apply to other competitive programming problems in general. And let's see, so Manuel asks a good question, which is, can you solve G2 using the birthday paradox and iterating through divisors? Yeah, so I like this question. So I think basically what Manuel is suggesting, and correct me if I'm wrong, this is actually the first thing that I tried before I came up with this solution, is we're going to just query a bunch of numbers, and then if we reach the same the same sector after I queries and J queries, then n must be a divisor of, like, if we let like k whatever be the k we use for the ith query, it must be a divisor of ki plus 1 plus ki plus 2 plus up to kj. And so then we can check the divisors. And I think the issue here is that this probably will be difficult to do in 1,000 queries, because with 1,000 queries, there are only 1,000 choose 2 equals, why am I doing this with a calculator? About 500,000 possible differences. And so it seems like unless we do this in a really clever way, we're not going to be able to hit all n. And so this might possibly be like workable for G1 somehow. In fact, like with G1, you could do something like this where, I mean, I guess our solution to G1 actually is pretty much equivalent to your idea, where for G1 we're going to query 1,000 times and 1,000 times. And then some interval is going, and then no matter what n is, there's going to be some interval within here that has total sum equal to n. And if we find the smallest such interval, that's going to be our answer. So that actually is one way that your idea, actually, you could think about this for G1. I think G2, you sort of have to get this randomness involved because otherwise it's just going to be you just don't have enough information to go off of with just 1,000 queries. Okay, and Jerry says, what is your process when you only have a solution of a guess of what the solution might be? How long do you spend proving the guess before trying it? So I think it depends. So I guess first of all, once you've done enough practice, you have a good sense of like whether something is provable, even if you don't have an actual proof. And so in that sense, like I usually won't write out a formal proof of everything I'm doing as long as I'm like pretty convinced that there is a proof out there somewhere. The other thing I'll say is that like the amount of time I'll try proving it is higher the more likely, like the more suspicious I am of the claim, and the more annoying I think the solution would be to implement. Because if I can implement the solution really quickly, and if it gets wrong answer, I know, okay, this was so easy to implement, I know I didn't make an implementation error, so I can just like spend 5 minutes to quickly test my idea, then like I will often just implement without and see if I can prove by AC. But on the other hand, if it's like I have an idea, but to implement it, it would take like a 45-minute really bashy solution, then I'll want to be sure my idea is right before I implement it. So that's like sort of the general framework I work under. Carvalho asks, can you try solving some introductory problems from the USSR Olympiad book? I am not familiar with that book, so I guess the best I can say is maybe. Ratan asks, can I purposely submit a code that gives the wrong answer for a certain test case with a different account and hack it with my original account? No, and the reason is that it's against the Codeforces rules, and so you will likely get banned. Okay, yeah, I'm going to check hacking one more time and see what's going on here. Okay, I think that's just about everything, so I'll stick around for if there are any last questions, and otherwise I will go ahead and turn off the stream. Oh, and NotLinux has a good point, which is that in contests where you actually get points for hacking, you aren't allowed to hack, you can only hack people in your room, and your room is like just randomly selected 40-ish people, and so even if you register with a second account, which again isn't allowed, that isn't allowed, but even if you did, that you probably wouldn't be in the same room, and so you wouldn't be able to hack it. Play on Piano asks, what do I think of Caret versus CF predictor? I like Caret, and the reason is that I think this like performance column is a really cool feature where you can see like what sort of rating is your performance on this contest equivalent to. Jerry asks, what happens if you successfully hack yourself? I don't think hacking yourself is allowed in Division 1 and Division 2, although I'm actually not sure about that. I haven't ever seen it happen, but who knows. In Div 3, I believe you can get credit for hacking yourself, but of course then you lose credit for the problem, so that probably isn't worth doing. Yeah, and it is like a common trick, and as NotLinux, another common trick for getting negative performance is to go into like a Div 2 contest and submit like a solution that is hackable, and then let's see, maybe right at the bottom, yeah, or even like a solution that isn't hackable, but then just make a bunch of really incorrect hacking attempts. And it looks like maybe, let's see, you might not be able to hack yourself in Div 1 and Div 2, because I think this person, I don't know if they intend, or I don't know if they just unintentionally got FST on this problem, but I don't think they were able to hack themselves. I have a funny story with about hacking, actually. So my very first Codeforces contest, I go down here. As you can see, it did not go that well for me. So what happened was I opened the contest, I pulled up the first problem, and the problem was, like, given n, you're supposed to print the last digit of 1378 to the n, and of course this is just so we know 8 to the, or this is the last digit of 8 to the n, which just repeats on the pattern 8, 4, 2, 6, 8, 4, 2, 6, and so on. And so at first I thought, great, like, this is a really easy problem, and but then it turned out that back in these times, this is Codeforces Round 383, which we're up to like 878 today. But back in those times, authors often like intentionally left edge cases out of the pretest to allow for hacking. And so what happened is I submitted my solution, and then I locked it just because I had read the Codeforces rules and I saw that locking was the thing, and I was like, sure, I guess locking is something you're supposed to do. And then this person, who now is a blue, looks like, submitted the 0 case, which was not in pretest, and hacked my solution. And then because I had already locked the problem, I couldn't resubmit anything. So, yeah, I think it's a good thing that things like this are no longer part of the Codeforces meta. And I'm actually curious if people got mad about this at the time, but that was how I got a 0, and then the next few problems were not things I was able to do, so I ended up all the way down here. So not a great start, but improved quite a bit from there. Yeah, I want to see, like, I feel like this might have been just yeah, I don't know if people actually got mad about this. This is also it was also kind of funny because this is back in the time when contests often didn't specify whether or not they were rated, which made things pretty confusing. Let's see. Where's the n equals 0 discussion? Did people complain about this? Yeah, it doesn't really look like people were complaining about all the hacking at the time, so I think that's maybe a new phenomenon. Resubmit it now. Yeah, you know what? We'll do that. Hold on. We're gonna finally solve this problem that's been eluding me for years. All right. Let's see. So let's see. So one is. So this should be what? 6, 8, 4, 2. The other really interesting thing is that back in this time there were almost no contests that had multi-testing like this. Like here you can see it was, even though like you could have a whole bunch of test cases and it would still work fine, it was just you read one case. And now I think because of queue issues, authors just aren't allowed to have problems A and B that don't have multi-testing. All right, we did it. Come full circle. Yeah. All right. Cool. Yeah. Thanks to the authors for the round. Overall, I think there are worse div 3s and better div 3s out there. There definitely was room for improvement in the clarity of some of the statements, particularly A, and I thought F and G were a little bit difficult to read, but there's nothing like egregious. And then, of course, I'm not a huge fan of how all of it seems like there were a lot of hack cases that were left out of the included tests, which is a little bit unfortunate, but all in all, it wasn't a bad round. The problems were definitely interesting. I thought G was a pretty cool problem. So yeah, I think that's everything, and so I will go ahead and turn off the stream. Not sure when the next one will be, because the next round is going to be after I've moved, and so there may not be time to stream that day, so we'll see what happens. But in any case, I will see you all next time, and thanks for watching.